with our study of the supply and demand curves. The reason we go through that is that it is used quite a lot in the literature, and if we don't have the background, it's hard to understand. Here is, for example, a justification of the demand response strategies developed in the paper mentioned here. Yes, mentioned here in this. Here, the motivation is essentially to reduce the reserve that is needed for coping with grid outages or generator outages here. And here, this is showing the supply curve, which is very typical of what you have in existing systems where you have a large linear part. It's all globally convex, but it's linear when the production is small. And then it decreases very steeply, and there would be an asymptote here, which means there is a maximum that the system can provide here. And the demand curve we see is typically close to a vertical line, which means it's largely inflexible, not 100% inflexible, but largely inflexible here. And this is showing what happens when the load varies. So at the peak time we are here, at the off-peak time we are there. Now I'm assuming the supply curve remains the same, which would be the case, for example, if we're based on nuclear and coal. And then we see the difference in price. When the load increases, this economic theory, which is the one implemented by many markets, will lead to increasing prices here due to an increase in demand here. But here, this is showing what applies, what happens if there is an outage. So like in one of the curves we've seen an hour ago, a 1 gigawatt generator has an outage, then the curve will shift to the left here, the supply curve. We've lost one big part, so we shift to the left. So we have that curve here. If the demand remains the same, then it may be that the price becomes much, much higher during the peak hour, which is exactly what we see. If we have a combination of peak hour and an outage, then the price will become very large. This is just a complicated way to capture the fact that we will be forced to explore the supply curve in the areas where costs are very high here. Now, what happens if I have a flexible load? Then instead of having a load that has this shape, I will have a load that will be more like this. And this will be able to bring the prices down. So one of the assumed benefits of demand response is also this one, which is if there is an outage that occurs at the peak time, then having some flexibility of the demand will be able to bring the prices down, which will now be a monetary benefit for everyone, at least on the short term here. This is exactly what has happened in this paper that we saw at the beginning. We saw that there were prices now not due to peaks, not due to an outage, but due to the unavailability of transmission capacity. And this paper is explaining exactly what happens. Here there is the supply curve given by this line here. The original demand is here, and the price emerges to that point there. Now, if we shift the demand, if we simply reduce the demand, we will obtain this price, which will be here. But in reality, what they have done in this experiment is to obtain what we called a minute ago the price-dependent bid, because the impact of their system is that users will stop using a number of things when the price goes above some level. So that will give this large discontinuity in the derivative here that will cause an even further reduction in the price here. So manipulating those curves here is what might be an alternative to building more transmission capacity. Transmission capacity means high voltage lines. Building another high voltage line is a major cost and also a major impact on the landscape. So if you can avoid that by having peak reduction here, that's of course a benefit. I mentioned the utility curves or the supply curves here. So here, some papers are trying to capture them quantitatively. So this is showing here, for example, how industrial users react to price. This is a logarithmic scale. So the curve is in fact varying much more rapidly than what is shown here, than what appears here. That is taken from this study here. So when you have industrial customers, of course, they are able to react exactly to the price that are offered. So if we plot exactly the price versus the quantity that they buy, so this is upside down. In the other curves I've shown, we have quantity on the X and price on the Y. So here, this study did the other way around. We see, of course, we don't find a nice curve, but we find a cloud that still indicates that we could be able, with standard curve fitting, to fit probably a linear line here in log scale, which means a power law for the supply curve. In fact, this is not the supply curve, this is the demand curve for the industrial customers here. So it is possible, at least for large consumers that manage their consumption rationally, to obtain those curves, and then it's possible to design a demand response program effectively. But of course, things might be a bit more complicated. This might recall you, this is something we've seen last week. Here, I've equipped this house with an energy management system, an EMS, that tries to adapt to the prices. Here we've seen there are 3 prices of electricity, which is probably things we will see in the future, or we already have in some areas. And we see that the effect is truly to reduce the amount of consumption at the peak hour. We see here when the peak is here, then there's no heating. We don't see the power consumption, but we can infer it by the fact that the temperature is dropping. So we see there's no heating at this period of high price. And at this period of medium price, there is only one heating event that occurs towards the end here. So we see that there is indeed some synchronization of the demand to the prices. But it's a bit more complicated than simply utility maximization. This is not maximizing the instant utility, it's using an MPC to maximize the utility over a complete horizon here. So we do see the reduction of consumption during high prices, which we can, if we have models like in the previous slide, we could even capture it quantitatively. But we see also something else. We see here that the price is high, but before the price is high, we see the temperature is rising, which means there is a consumption here. So we see that before the high price, in fact, there is a change of the load. So it's an important effect, which in that case is called the pre-bound effect. At least some papers use that terminology, which means that if we do a demand response in some period of time, this will have an impact to the period before in that case, because we have an MPC. In other case, it will be after. With Voltalis, if you stop the heating during 1 hour, then as soon as this 1 hour is over, all heaters will start again. So there will be what is called a rebound effect. After the heating, we will have more consumption. So that's another effect that's important. We are simply shifting the consumption. So by shifting them, we're not getting rid of them. Again, that's not the goal of demand response. It's to shift to appropriate periods of time. This paper here is in fact going a bit further, and it has analyzed behaviors in a simulated but fairly detailed simulated model of the power consumption of a number of devices at the scale of the state of a complete state in the US. And here it's showing demand response event, which is a period here of high price, and it's showing the power consumption, the total power consumption of different devices. Here, of all the devices, we see that during the demand response event, which you can interpret as a period of high price, there is indeed a reduction. But here the time scale is hours, so we see the reduction lasts for perhaps 20 minutes. And then after that period, there is again an increase that is, of course, much less than what would have been if the peak would have occurred naturally. But still, there is an increase here. And when the demand response period stops, when the demand response event terminates, there is all of a sudden an increase here, which is the rebound effect. So how do we interpret that? Well, we can interpret it by looking in more detail at what are the consumptions here. So here, this dotted line is AC, means here air conditioners. So this is US study. So most of the consumption is due to air conditioning. And we see that you can stop the air conditioning for perhaps 20 minutes, but after 20 minutes, the temperature rises, which means houses are very poorly insulated, which is invariably the case in the US. They don't even have shutters to prevent the sun from coming in. So of course, the houses are heating up very quickly. So after 20 minutes, the air conditioners are up again to their normal level. But you have other systems that are submitted to demand response. You have here fridges that may resist for a larger time, much more. But you have also what is called slow water heaters. So slow water heaters are heating systems like we have more in Europe that are boilers or other systems that are used for heating space that have a much larger inertia. So they're able to be stopped for perhaps 2 hours. And you have other things here, special to, I think this study is about Florida, pools. So the swimming pools, people have houses with swimming pools, and every swimming pool has a filter with a fan that rotates. So it's a bit like a fridge. It's running all the time at low power, but it's constant. And there are probably tens of millions of them in one state. So you can also control them. And those are things you can really stop for 2 hours without problem. So we see two things. We see that load shiftings are limited in duration, and this is regardless of price. Even if the price is low, then the air conditions have restarted. And second, the user reaction is largely independent of the intensity of the price signal. It is not because the price has reduced by 50% that we reduce for 20 minutes. It is because the price has reduced, we reduce and stop the air conditioners for 20 minutes. So it's a fairly binary response. We reduce or we don't reduce, and for a limited amount of time. So that all tells us that the very simple economic theory that I've given to you needs perhaps to be made more sophisticated, which is what is done in papers like this. So here you need not just a user model that assumes that a user is simply reacting as an instantaneous utility maximization, but you may want to model, for example, the thermal load, the fact that the user is using this energy to do something, which is to bring an adequate temperature to a house or to an amount of water. And if that is the case, then you want to model this. You want to model the thermal load, not the user as a utility maximizer. Other critiques have been formed of the theory of demand response. Well, this paper has studied a demand response experimental program that was deployed in the UK for industrial consumers. And in fact, when you subscribe to a demand response program as an industrial consumer, you have to give a guarantee. You have to give the guarantee to the aggregator, the entity that does the demand response, Voltalis, for example. You have to give the guarantee that you will follow it. In the case of Voltalis, that's easy because it's Voltalis who puts the device on your, that puts the relay. So Voltalis controls it. But if you are now talking to an industrial site, and this industrial site will say, well, I will use my heaters a bit less to produce aluminum, for example, if you send me a signal to reduce the consumption. But of course, you must have a contract. The demand response company will monitor that you do really reduce the generation. How can you do that contractually? Well, it is in order to reduce, and you use backup generation. In fact, a motivation for many industrial companies to participate in demand response program is a bit contorted, is the following. Many companies depend on energy on reliable energy supply, so they have backup generators. That's the case, for example, of all telecom providers. So the telecom centers for Sunrise, Swisscom in Switzerland, they have backup generation so that if they lose power, they will be able to continue providing power, at least in theory. Then those companies are saying, but we have those diesel generators that are here. They work only in case of power outages, which are rare events that happen perhaps once a year for a few hours. So could we make use of this generation? Yes. And the way they make use of it is by participating in a demand response program. If the company asks me to voluntarily reduce my consumption, I can do it because I have diesel generation. And if the cost of diesel is less than the benefit I receive from the demand program, I will participate. And this study has shown that, in fact, the CO2 benefit of such demand response program is marginal or even negative because of this problem here. So that is something to be aware of. As soon as we touch the grid, we touch a complex system. Hopefully in the future, many companies will use backup generation in the form of batteries. A number of systems and companies are starting to provide such services. And then once you have a battery that you can use as backup power, you can also use it to provide regulation services. I've shown an example with the microgrid on the EPFL campus that provides primary and secondary frequency support. That's an example. This battery could be present because we need it for a data center, for example, for backup. And if we have it, then we can also participate in supplementary services. Another side effect is that if you think of a company like TICO or Voltalis, at least so far in Switzerland, global warming has not been such that we need a lot of energy in the summer. Therefore, the only way we can reduce what the heat pump is doing is in the winter. So we have no way to provide regulation in the summer. But even in the winter, if for some reason there is a very hot day, then nobody is using, or not enough people are using the heat pumps. If there's a very sunny and hot day, and this can happen even in February, the whole park of the TICO heat pumps are not working most of the time. So imagine at the same time, for some reason, Swissgrid is sending a secondary regulation signal to TICO that needs to reduce its consumption. But it cannot reduce its consumption because all the TICO controlled heat pumps are not consuming. So it has a problem. So what does TICO does? What some demand response aggregators do is they buy diesel generators. This is what those guys are doing here. TICO, the way it solves it is buying shares into a hydro producer, and then it will sell those, activate those hydro shares to produce more instead of simply reducing it. So you see one of the side effects and potential difficulties of demand response as long as we don't have a large deployment with, for example, batteries. Voilà, that is about the economic theory of demand response, which, believe it or not, is the main theory behind many regulatory and economic deployment of demand response. Now, in the rest of the lecture, I will address two topics which are also important, at least for this one: elasticity. So elasticity is the question that we have seen already. Assume in gray is the natural load. This is the load that we would have in the system. Now, if I want to do demand response, I would like to obtain the red curve. Is it what we will really get? That's the ideal that we should have. This is what the economic theory of utility would show to us. But in reality, will we not get this here? So this means a rebound here. And if the rebound is larger than what we had here, in fact, we might make things worse. So we need to capture this rebound effect that we have already discussed. And this is exactly what has been observed here, for example, in some companies in the US who've done demand response events. They've observed really this. They've observed that, yes, we are able to reduce the load, and here it's essentially air conditioning, but we have to anticipate the fact that when we stop reducing it, we have an increased consumption. So if this increase may go beyond the peak that we're able to sustain, it might be worse. So you need to manage this increase potentially by making sure you don't stop everybody at the same time, for example. How do we capture this? Well, one paper proposes this. It's a paper of 2000 by Kirschen and company in the UK, where they capture what is called cross-elasticity coefficient. So they say, if I do a demand response event by price, I have a delta on the price at time t plus h. Here, to simplify, assume t is in hour. So that's what we had seen in this Norway pilot here. I must, before managing my demand response event, I must capture those coefficients that are capturing how much a difference in price would affect the difference in loads. So the load at time t will be modified by a change of price at all times before and after the time t. This is a pre-bound and the rebound effect here. So you need a way to capture or hypothesize these coefficients. So those coefficients are the delta at time t that is due to a change of price at time else. Here. The model is lossless if the sum overall t of a reduction in price at time s is 0, which means we have pure shifting of loads. If this is not the case, if it's positive, then this means we have negative losses. So the demand the demand response event might cause an increase in consumption. If it's negative, we will have a true loss of loads. And it's not very clear yet what is happening here. So this is the cross-elasticity coefficient that is useful in the context of demand response. There are multiple definitions of cross-elasticity. This one differs from the traditional one, but it's the one that makes sense in this context here. So let's see here what is in this paper. This paper has done a what-if analysis. It has not measured these coefficients, although we could measure them by smart meters, by doing a number of experiments and seeing what is the differences in loads when we change the price in some way. So this is what smart meters might give us in the future with big data analysis. Right now, what they've done is a pure hypothetical analysis. So they've assumed two scenarios, two types of user behavior to response to price. Here, they've assumed that these first users are only shifting a little before or a little after. So here, the 3 hours before the time the event response event causes a small reduction, a shift, and it's lossless. So 20% of the load is reduced by having a demand response event times the price, 0.20 times the price difference. And this is shifted uniformly before or after. So this is what we could call inflexible users. They still react to demand response, but they insist on having the thing done exactly at the time they wanted to do it. So it's inflexible because the user is inflexible, or because you have a thermal system that cannot afford such a high inertia. And then we could assume here we have more highly optimized systems that are able to react very strongly to the price by shifting it over a period of 24 hours. Here, that would be the periods of the hours of the day where the prices are low, which are outside the peak hours that I mentioned before. So they transfer to early and late hours of the day. Perhaps it's doable for washing, but perhaps less doable for heating. And in both scenarios, it's lossless. So if we think again about how the price is affected, so the goal of this paper is to look at the impact of price formation. What is the impact of price if users react in this or that way? Remember, we had this in Norway. We had this price problem due to transmission capacity. Here, it's similar. We know how to model the price formation. So this paper has used supply and demand curves and uses that to study the formation of price, and has done simulation to see, for example, what are the prices. Those are the normal prices in blue here. And what are the prices if there is an outage? If we lose one nuclear power plant, this is how the prices will go up. Today, for most of us, we don't see those differences. If the price goes up because there's a loss of a generator, it is our energy provider, Service Industriel de Lausanne, that indirectly will have to live with that, depending on the kind of contracts we have. If we start, but this is not the case of industrial users. For example, industrial consumers are exposed to price variations, and in the future, we might be exposed to some of this. So they assume, through the study of these supply and demand curves, that if I know the demand Q, I can obtain the prices, given some assumptions about the supply here. And now, since the demand can vary based on price, that's what we do with demand response, we can also say that if the price varies, I can obtain some function g of the price here. And this is obtained by having their cross-elasticity model here. So they don't do it using the simple utility curves, but using this cross-elasticity model. Now, if we combine the two, if I know the price, I can obtain the demand, but if I modify the price, I will have a new demand. So I can solve this for a fixed point, hoping the fixed point works. And then I can do hypothetical things of saying, given a given state of generation, what would be the prices here? So this purple curve is the prices we had. This is the price that are obtained in the case where there was a power outage here and no demand response. And now the yellow and the green curves are the prices we obtain with the two different models of customers. The yellow one is the one where customers shift their loads in the 3 hours before or after uniformly. Then we see that truly when there is a peak in price here, that can be interpreted as a demand response effect. There is a surge before, that's the pre-bound effect, but we see also that there is very quickly after rebounds effect after. In fact, during the demand response event, because those loads are able to follow, but only for some amount of time. And in fact, we see that the peak price even gets worse. So the peak price is higher with demand response. So that's the difference between the utility approach, which will never produce such a result, and this cross-elasticity coefficient approach, which shows that, well, depending on how the elasticity is, if there's not much elasticity, forcing the prices to be high for a long period of time might have an even worse effect. Of course, if we have users that are very able to optimize and really take long differences in time, this will not happen. So they're able to move all the loads to the periods of the day where that may be very far away. So early morning for something that you were planning to do in the afternoon, then this problem will not occur. So take home message, scenario one does not smooth prices. If you look at the details of the paper, it says that the average price is still reduced. So, but still the high price here indicates that there is probably a supply difficulty. So care must be taken with demand response program to manage the pre-bound and rebound effect and correctly capture the elasticity coefficients. That's the take-home message from this. Now we will conclude with a perhaps more anecdotal topic, which does not have such a high economical and grid control impact as the cross-elasticity issue. But I did not resist to do it because it puts together all the elements we have seen. That's the issue of the loss of load. So loss of load, which is also called evaporation, is a fraction of energy that's saved to demand response. So here we consider that energy is the same whatever time of the day we produce it. And the question we ask is there a loss of load by doing demand response here? Which is intuitively what Voltalis is assuming, because Voltalis is saying if you do implement your R stuff, you will pay less. And Voltalis is in settings where prices are constant. There's no time of the day pricing. So if you pay less, that means because you consume less. So here I'm showing the natural load. That's the integral. The energy in gray is what we would consume if there's no demand response. Now, if there is demand response, we know we consume less during the peak, but there will be another peak that is triggered by demand response. And the question is the pink integral less than the gray one, and by how much? And that's important to know. if you are dimensioning an energy system. In fact, this is related to the question that the happy of you that have a chalet in the Alps must consider. If you have a vacation house in the Alps or on the Bornholm Island that you don't visit very often, what is the best? When you're away, should you keep the heating on? Of course, you want to keep it on so that it doesn't freeze if you have water pipes here. So, but if we exclude that question, your goal is simply to have your chalet hot when you return. So assume you have a radio controlled system that you can activate remotely. Is it better to activate it remotely just before coming, just before arriving, or should you keep your house warm at all times? What do you think? Okay, I have lost mood. Speak up. Try again. Voila, here we are. Let's close the poll. The majority of you would not heat your chalet during your entire absence, which is probably wise. As we will see, yes, there will be a reduction in total energy consumed. And to see why, first, let me recall that here we're really talking of the loss of load and not the rebound effect, right? So the rebound effect is there will be a higher energy consumption when you heat your chalet before you return. But that's not the question we're asking. We're asking whether the integral is larger. For this, we can simply use the simple house model we had before. The same conclusion will true if you use a more sophisticated model, but this house model will give us the true reason here. Remember from the house model that we used last week, that energy that we put into the house, bought from the grid, converted through the heat pump, or directly through a resistance, is put into two places. It's put into the air. This is captured by the leakiness, the outside air, or into the walls and the furniture and the inside air. This captures the inertia. If you think about it, the equations are the same as the equation of a leaky bucket, where the temperature takes the role of the level of the leaky bucket. The heat that goes in is what you put into it, and the leak is how much goes out. You will have exactly the same equations, which is a useful image. Now I will compare two scenarios. I will look over some period of time, all the energy that is put into my system, and I will compare that to what happened to the right-hand side of my equation here. I compare two scenarios, one with no interruption, so the one you don't prefer, where you keep your house warm all the time. So if I keep my house warm all the time, that means my target temperature is the value of the house is always the target here. Right? Then the heat, the integral of the energy that I've used is equal to that, and we can split it into two parts. The part that has been used to keep the house warm, and the part that goes out. But if we do the integral, if we look at this, everything that I've put in is either inside or has gone out. Since the level at the end is the same as the level at the beginning, I keep as the target temperature period, everything that I've put in is what's gone out. So the whole heat I've put into the system in this simple scenario is simply heat that's gone out into the air. Now, if I compare to the other scenario where I don't heat, I will heat more when I come back, and in between, I will let the thing go out. But the same conclusion applies. Since the level is the same at the beginning, at the end, that's the temperature when I left my chalet, that's the temperature just before I return, we have the same thing. The integral of what I've put in is equal to what has gone out. The difference is the difference in level, which is 0 here. So in both cases, the integral of the heat that goes in is what goes out. So now we need to compare what goes out. But here in this simple model, and this is true even of more sophisticated model, if the inside temperature is larger, the leak, whatever goes into the outside, is larger also. If my chalet is at 20 degrees, then the heat transfer is larger than if the chalet is at a lower temperature. In the worst case, in the best case, if the outside temperature is equal to the inside temperature, there is no heat transfer. So in this case, we expect the leak to be less because the inside temperature is less, which is what we can check mathematically instead of by image. We will see that the energy that we put in is less here. So take-home message. If we interrupt the heating, we reduce the temperature, but we reduce also the energy consumption, even if we restore the temperature by having a rebound effect after the event here. So this was not a demand response, but we could imagine this is a demand response effect. This is what we would have here. Now, what I said about Voltalis has been checked by a French governmental agency. That's the agency that takes care of energy in general. And in their report, they said that it's true that with Voltalis load switching system, users save 10% of heating, but nothing on hot water, nothing on boilers. So this is what macroscopic statistics on users give. How do you interpret this? I close the poll in a few seconds. And 100% thinks B, which I also think. It's not very scientific to just think. We would need more studies to see why. What we can do is at least a thought experiment. Whoops. And the thought experiment could be the models we have. We see that if I have a resistive heating system with a poorly insulated building, by reducing the temperature, and this is what Voltalis will do, it will reduce the temperature a bit within the comfort zone, but still will reduce it, then you will have some loss of load. And this ADIME report says it's about 10%. So there is really a loss of load, which is true here, at least for resistive heating. Of course, you could say, and this is why Voltalis customers are happy, of course, what Voltalis doesn't say to these customers is that if you would reduce your thermostat by 0.5 degrees, you would get the same thing, and perhaps even more, and you would not provide support to Voltalis. So that's why they don't say that. Now, this is not always true. So the issue of loss of load is, of course, not necessarily has to be taken care of with care. In particular, if you don't have a pure resistive system with heat pump. So this is why the statistics about TICO are less well known, and I would be curious to know what happens. If you have a heat pump, you have a nonlinear system. The coefficient of performance or of efficiency depends on many things. It depends in particular on the outside temperature. So now if you decide to use your heat pump at a different point in time, if you do it when the outside temperature is very cold, then your heat pump will need more energy to provide the same amount of heat into the house here. So if you have heat pumps, you need to be more careful and make sure this does not happen. So when you delay your heat pumps, you have to make sure when you delay exactly, and you don't do it at periods of time that would deteriorate significantly the coefficient of performance. Boilers are probably a case. Boilers are typically well insulated, so it's probably true that if you boil your hot water from 2 to 3 in the night or from 5 to 6, it probably has an effect, because insulation is never perfect, but the effect is probably extremely small, so it's not visible in the statistics here. In the future will tell us whether there is something important on the side of electric vehicles. If you purely shift the charging of an electric vehicle, probably there is no loss of load. But if you do fast charging, there is probably negative loss of load. So the resistive losses will be not negligible. So this is an example where managing the load dynamically might have an impact on the peak that will need to be taken care of.